The topic of synchronous machines continue, and here we have the example. The synchronous machine in example 6.3 is operated as a synchronous motor. So this is a problem that is dealing with synchronous motor, and this is the power supply. Now the field excitation is adjusted to the so that the power factor is unity, because you know that through field excitation we are able to control the current and voltage, terminal voltage and armature current or the line current angle, and the machine is drawing a 3 kilowatt power from the supply. So the first thing it requires is what is the excitation voltage, the voltage that is generated inside the machine, and what is the power angle. Power angle is the angle between the our terminal voltage and the voltage that is generated inside the machine, and we are required to draw the phasor diagram for the condition. So let's look at what was the machine in example 6.3, and this was the machine in example 6.3, which is now and the critical information was that the winding resistance was negligible and the synchronous reactance for the machine was 8 ohms. And so we can start solving this example, but the first it has told us that for example this was our machine, and this synchronous machine is acting as a motor, and let's make it a motor so there is no confusion. And the real power, this is our machine, and it is drawing 3 kilowatt of total power. For the total power, the real power that is absorbed, this is in watt, so it is real power. The formula for the real power, we know that P real is actually equals to 3 times V terminal IA cos of phi, where this V terminal is actually phase voltage. This is a phase voltage as it is a Y connected machine. So this is actually for the machine. We know that EA and RA is 0. We have X of S, that is 8 ohms, and this is actually V terminal, and in this scenario it is acting as a motor. So we know that current will be flowing inwards into the machine. So we can write that 3 Vt Ia cos of phi is equals to 3 kilowatts, and we know that from the previous example it was but if you don't remember, here we have 208 volts for a while connected source is actually line to line voltage, and we converted this to phase voltage by dividing this by under root 3. This was 120 volts with the angle 0, that is our reference angle. So this is 120 volts, and cos phi is what? Cos phi would be, here it is saying that the field excitation is adjusted so the power factor is unity. That means it is 1, cos phi or cos theta is 1, and so by knowing these values we can calculate the value of Ia equals to 8.33 amperes. Now this is 8.33 amperes, and we also know that the cos theta is 1, or here I have written, okay, let's make it cos theta. So students don't, cos theta is 1. So this, the angle of the current is actually Ia equals to 0 degrees, same as that of the voltage. Now to calculate what is our question, find the excitation voltage and the power angle. So what is the excitation voltage? Excitation voltage is this EA. Now let's apply KVL. Let's apply KVL to this circuit, and what we will get will be EA is actually equals to VT minus IAJXS. So the terminal voltage is 120 volts and we have the angle is 0, minus IA is 8.33 amperes, angle 0 degrees, and for XS it is 8 ohms, with because of J it is 90 degrees. And by solving this, the value of EA that we will get will be 137.35 volts with an angle of minus 29 degrees. And we can see that this is per phase value, and the power angle is actually the angle between VT and EA, and here we can see that this is minus 29, so our power angle is minus 29, and this minus angle also shows that it is now performing as a motor action. When the power angle is positive, this is for the generator action. Let's see in the previous example when we performed here, if we can find the power angle, here it is, when the machine was acting as a generator. Now the machine is acting as a motor, so the power angle is negative, and if we want to draw the phasor diagram, the phasor diagram can be drawn. This is, for example, our VT, angle is 0, and the angle for the current is also 0 because the power factor is unity, so they are in phase. And we can see that, so VT, and this will become IAJXS. This is actually IA minus IAJXS, and this is actually the value of EF, and this angle is minus 29 degrees, and this is actually the angle between VT and EF is actually delta. Okay, so the next part says that if the field excitation is held constant, field excitation is the part where the rotating magnetic field of the rotor, now it is saying that it is held constant and the shaft load is slowly increased. That means we have increased the load over the shaft. Determine the maximum torque, pull out torque that the motor can deliver. Maximum torque that the motor can deliver or produce. So if you remember in the one of the previous examples, I have explained you the formula of the power transfer, maximum power transfer between the machine. It is actually the SP is 3EA VT over X sine of delta. And for the maximum power condition, we consider that delta is 90, and this will be the maximum power that the machine can deliver. That is the stability limit. It is also for the motor, it is known as the pull-out torque. That means after we increase the torque beyond this value, the motor will start to slow down and stop down. So for the part B, and if you look at, we are in search of how much maximum torque can be produced. So for the formula, the general formula that you should know for the power is 3 VT IF, that is terminal voltage, and the internally generated divided by synchronous reactance sine of delta. And in the case of maximum power, This sine delta is actually equals to 1, where delta equals to 90 degrees. What is delta? Angle between Vt. If this is Vt, here will be Ea. This will be the condition for maximum torque for the machine when Ea will be like this. So for P max will be then 3 Vt Ea over XS. This is actually Vt we know is 120 volts, and what is Ea? Ea is 137.75. We have calculated here. This is the value of Ea, and X of S is 8. So by substituting the value, the P max would be 6180.75 watts. This is the maximum power. And he has asked us about the torque, the maximum torque. So for the torque, we know that T max is actually equals to, we know P mechanical, the formula for P mechanical is torque into speed. Speed, remember, is in radians per second. So T max over omega synchronous, the synchronous speed. And from where can we get the synchronous speed for the machine? And so the formula for our synchronous speed will, we should first know that this formula for synchronous speed is 120 F over P, where the frequency here for our machine, it is getting in the given in the question 60 hertz, and poles, the 4-pole machine. So N synchronous for our machine is 1800 RPM. This is the rated speed of our motor, that is the synchronous speed of our motor. And if we put these values in this equation to calculate the maximum torque, it will become 6180.75 divided by 1800 over 60 into 2 pi. This is actually 2 pi by 60 to convert this into radians per second. So the maximum torque that our motor can produce now is 32.8 Newton meters. This is the answer. I hope it helps. Thank you.